Hey there! In this video we're going to look at some limit properties and then use them along with some other concepts and techniques to evaluate some limits analytically. Alright, before we start thinking about these properties more generally, we're going to look at what's going on here with a couple familiar functions. So think about the function y equals x squared, one you're familiar with. How can you use what you know about that function, like the graph, how the values go, to determine the limit as x approaches a given value? For example, say you were looking for the limit as x approaches 3 of x squared. How could you figure out what it is? Well, if you just picture the graph of that function in your mind, first of all, you know that when x is 3, y is 9 for that function. But what you maybe haven't thought of before is, as the values get closer and closer to 3, the y values get closer and closer to 9 from either side. Because y equals x squared is a nice continuous function, as x approaches 3, the y values are going to approach the same thing as the value at 3, which is of course 9. So if we want to work out the limit of x squared as x approaches 3, we can just determine the value of x squared at 3 by substituting the 3 in, so 3 squared, which is of course 9. If we look at another function you're certainly familiar with, y equals 2 to the x, if we want to determine the limit of that as x approaches 3, again we can think about what we know about the function. Y equals 2 to the x is a nice continuous function, so the values of y as x approaches 3 are going to be the same as the value of y at 3, which for that is 8. So to determine the limit as x approaches 3 directly, we can just work out the value of 2 to the x at 3. So substituting the 2 to the third power is 8. This property that we're using here is actually called the limit property of substitution. And what that says is, if you know the function is continuous at the point you're interested in, x equals a, then the limit as you approach a is going to be the same as the function value at a. Or the way you'll likely end up remembering it with words is, if you know that a function is continuous at a point, then you can work out the limit by substitution into the function. Now we're going to build on that to determine some more properties of limits. Let's think about the function y equals x squared plus 2x. Now you likely have never graphed that function and you don't have a picture of what it is in your mind, but let's say you wanted to find the limit of that function as x approaches 3. Well, because that function is made up of two that we are familiar with, and we just worked out the limit of each of those, as in, if we know the limit of x squared as x approaches 3 is 9, and the limit of 2 to the x as x approaches 3 is 8, and we know that the function we're looking at now is just made up of those two individual components added together. If we want to work out the limit as x approaches 3 of x squared plus 2 to the x, because we know the values for this function are just the values of the individual functions added together, we can determine this limit by adding the two individual limits. So this limit is just going to be 9 plus 8, which is of course 17. This is one of another set of limit properties based on what you know about function operations, and so we often call these limit properties of function operations. Our function here that we just looked at, we knew was made up by adding two functions we were familiar with. And what we actually used was the limit property of addition. And what that says is the limit of a function that's made up of two added together, f of x plus g of x here, is equivalent to the limit of each function individually. So the limit of f of x plus the limit of g of x. That's what we did there. The limit of a sum is the sum of the limits. Our situation, we wanted to find this limit of this function, two functions added together, so we just added the limit of each separate function to come up with the limit for that combined function. Now you might have already predicted what some of the other properties are. The second one is for subtraction, and similarly to find the limit of functions that are subtracted, you can just subtract the two individual limits. The limit of a difference of functions is the difference of the limits. For multiplication, the limit of functions that are multiplied can be found by multiplying the individual limits. The limit of a product is the product of the limits, how you say that in words. For division, if you were looking for the limit of functions that are divided, you can just divide the limits of the two individual functions. And as is often the case with division, we need the additional condition on here that the thing you're dividing by is not 0. So the limit of g of x can't be 0. The limit of a quotient is the quotient of the limits. For powers, the limit of a power of a function, if you have f of x to the n and you want the limit as x approaches a of that, you can find it by taking the nth power of the individual limit of f of x. The limit of a power is the power of the limit. And this works for roots as well, because of course that exponent could be 1/2 or 1/3 or any fraction which would represent roots. So in this case, square roots, cube roots, or any other root you can think of. This one also has a condition we have to add on, that n has to be greater than 0, because for reasons that you'll understand more as you move forward with limits, that power has to be positive. Last, we have the constant multiple limit property. So if you're looking at the limit of a constant multiple, k times f of x, you can work that out by multiplying k times the limit of the individual function. Another way to think about it is, if you have this constant in here, you can kind of pull it out and then just multiply it by the limit of the individual function. The limit of a constant times a function is the constant times the limit of the function. Now, I know when you look at a list like that of properties written in a very abstract, theoretical way with notation like that, you might start to panic a bit. But you should know that these are just properties that you're going to use when you're working with limits analytically. You're going to get to know them and understand them without having to memorize them in this formal mathematical notation. So don't worry. Now we're going to see if we can use these properties to work out some limits analytically. All right, so if we want to work out a limit of a function like this, altogether likely not something you've seen, but made up of components that we can work with, 2x plus 3 and 2 sine x over x. So we can write this limit instead as two separate limits, the limit as x approaches 0 of 2x plus 3, and then add the limit as x approaches 0 of 2 sine x over x. The first one, we can just use the substitution property because 2x plus 3 is a line, nice and continuous, that function there. So we can just substitute in 0, and we'll have 2 times 0 plus 3, which is of course 0 plus 3, which is 3. As for the other part of it, this limit, we're going to rewrite it, specifically this 2 here. We're going to write this as the limit as x approaches 0 of 2 times sine x over x. And the reason we're going to do that is because this 2 now we can put outside because it's a constant times a function. So we can write this as plus 2 times the limit as x approaches 0 of sine x over x. And then this whole thing is going to equal 3 plus 2 times the value of this limit here. Now, if you think about it, that function sine x over x we've seen before, and we know that that value is 1. This is going to be what we call a known value, and we can just replace it with 1. And then so the value of this limit is 3 plus 2, which is of course 5. Even though we don't know what that original 2x plus 3 plus 2 sine x over x function looks like, we know that as x approaches 0, the y values approach 5. In general, when we determine limits analytically, there's a variety of things we can use. First of which is what we saw right off the top of this video, which is using the idea of substitution if we can, if we know the function is continuous at the value we're looking at. Next thing we're going to look to use is any algebra techniques and skills we have, including what we know about trig identities, things you've learned in previous math work. As well, the limit properties we saw earlier, we're going to use those, of course. And then known values, like we just did with the limit of sine x over x at 0 being 1, things like that. And then as we move forward with our work with limits, sometimes we're going to use what we call numerical thinking about how values change. We're not really going to use it here, but it's included in the list for the sake of completeness because you will use it in your future work with limits. Now we're going to draw on that list of techniques and work out some limits analytically. This first one here, that polynomial, we can use substitution because all polynomials are continuous for all x values. And so for all polynomials, the limit will be the function value. Or in other words, the limit as x approaches 2 is going to be equal to the function value at 2. So using substitution, this limit is going to be equal to 2 cubed plus 4 times 2 squared minus 3, which is of course 8 plus 16 minus 3, which works out to 21. That's the value of that limit. Let's try the second one here, this rational function. And rational functions are continuous everywhere in their domain, so this is going to be the same as for polynomials. If the x value can be substituted, that's how we're going to work out the limit. As long as it's not a non-permissible value, that is going to be possible. So then by substitution, this limit is going to be equal to 1 to the power of 4 plus 1 squared minus 1 over 1 squared plus 5, which is on the top 1 plus 1 minus 1 is 1, and on the bottom 1 plus 5 is 6. So that limit of that rational function is 1 over 6. So the next one we're going to look at here, this rational function here, and trying to find the limit as x approaches 1. The problem with that is because of this factor on the bottom, 1 is a non-permissible value. So we're not going to be able to do it by substitution directly. What we're going to have to do is rewrite the limit and see if we can do some algebra to make it so that it's going to work. We can factor the top, that trinomial factors to x plus 2 and x minus 1. And on the bottom we have x minus 1. So then that limit can be rewritten if we cancel that common factor as just the limit of x plus 2 as x approaches 1. And that we can substitute it in. So then that's just going to be equal to 1 plus 2, which is of course 3. The reason this works here, and we can use algebra to simplify this, is this function here, rational function, with that common factor. All that common factor does is cause a hole in the graph at 1. And when we cancel that common factor and make it just x plus 2, we have a simpler equivalent function, the only difference being we've removed that discontinuity and it has a value at 1 instead of a hole. That's why substitution on the limit of the simplified function gives us the limit of the original function. And one last thing we should look at here before we leave this one is notice that I continued to write limit for several steps here, but then stopped writing it here in this step. That's because at that step, that's when I was actually evaluating the limit. In the steps before that, I was just writing equivalent limits here and here, but it wasn't until here that I substituted the value to actually determine what the limit was. I bring this up because it's a common error that you see where people aren't sure when to keep writing the limit and when to stop writing it. Once you've evaluated the limit, that's when you stop writing it. In this next one here, we're not going to be able to use substitution on this function because of this denominator here being 2x. At 0, that value is 0, and you can't have the denominator 0. But what we can do is write an equivalent limit and do some algebra. So limit as x approaches 0. Because the denominator is a monomial, I can split it apart into two fractions. So I can write 4 sine x over 2x, and the other part, of course, is going to be limit as x approaches 0. But that is going to be 5x over 2x. The two terms on the top split with the single denominator for each. And now that I've split that single fraction and split it into two limits, I can work on each one separately. So the first one, I can cancel the 4 and the 2 and just make it 2 sine x over x. And then the second one, limit as x approaches 0. But I can cancel those two x's and just make it 5 over 2. And then as I move on here, this first limit, this 2, we can pull outside because it's a constant. So we can say that this is equivalent to 2 times the limit as x approaches 0 of sine x over x. And this second limit here, think about this. This is a constant here, 5 over 2. Its value is always 5 over 2, no matter what the value of x is. Think about the graph of y equals 5 over 2. It's just a horizontal line, all the points where y is 2.5, 5 over 2. So no matter what the value of x is, y is always 5 over 2, or 2.5. And so we can write the value of that limit as 5 over 2. And then we can work on this first part. We have 2 times this limit that's a known value. We've seen it before. We can just say that the value of that is known to be 1, plus our 5 over 2. At this point, you can just work out what that is and write your final answer. But I'm going to put a step in here where I write this 2 as 4 over 2, plus my 5 over 2, which gives me 9 over 2. And that's the limit of that original function at x equals 0. This last one here, I'm going to say right off the bat, this one is a bit tricky, but we're going to work through it anyways. What we're going to do here to start with is write an equivalent limit for this, but we're going to take this tangent that's on top and use a trig identity to write it as sine 4x over cos 4x. And then, of course, that whole thing divided by x. And then we can take that and write another equivalent limit as x approaches 0. But we can write this sine 4x over cos 4x, and instead of dividing it by x, we are going to take this divided by x and write it as multiplied by 1 over x. Dividing by something is like multiplying by the reciprocal. What that allows now is when we rewrite it again here, we can make a few changes here. This sine of 4x and this x, I am going to write as a single fraction, because when you're multiplying fractions, you're just multiplying the tops and the bottoms, and it doesn't matter. You could switch those denominators. That 1 over cos 4x, I am going to write this as 1 over cos 4x separately like that. The reason I did that is because this expression here, sine 4x over x, looks quite a bit like the expression whose limit we know as x approaches 0 that we've already used a couple times, and that is sine x over x. The thing you may not know, and the trick here, is that if this said sine of 2x over 2x, or sine of 4x over 4x, it would also have a limit of 1 as x approaches 0. If you look at the graph, you can see why this is. For sine x over x, you know that that limit is 1 as x approaches 0. But what you probably haven't seen before is if you make this sine of kx over kx, if you replace x with kx in that function, all it does is cause a horizontal expansion or compression. In this case, when this is a 4, it causes a horizontal compression. That changes the y values for all of these points, except when x approaches 0, that value of y, or the limit, is still 1. That point doesn't change. And so if we can write an equivalent expression here, where we have sine of 4x over 4x in our limit, we can use that fact that it's 1. And to do that, we're going to multiply the top and the bottom of this by 4. And what that does is give us our 4x that we need on the bottom, and then this 4 on top, it's a constant times that function. We can put it out in front. And then this sine of 4x over 4x is what we're looking for that we saw in the graph. It's a known value. And then that function's multiplied by this 1 over cos 4x, but that we're going to be able to use substitution. So we'll write one more equivalent limit here. 4 times the limit as x approaches 0 of sine of 4x over 4x, and then that times the limit as x approaches 0 of 1 over cos 4x. So we have 4 times this limit that we know and we saw was 1, so we can replace it with a 1. And then this limit of 1 over cos 4x here, we can use substitution on that, because when you substitute in cos 4 times 0, that's going to be something we can evaluate. So we have 4 times 1 is 4, and then we have times 1 over cosine of 0. And then we're almost there. 4 times 1 over cosine of 0 is 1. And so then we have 4 times 1, which is, of course, 4. That's our limit of that original function that we started with there. If you wanted to, for this one or any of the ones we've done, you could graph the original function and then look what happens to the y values as x, in this case, approaches 0, and you'd see that the y values approach 4, even though that function would be undefined there. So hopefully now you have a good understanding of the limit properties and the other techniques and things you can do to work out the value of limits analytically.